Good evening. I'm Rahul Chaudhary. I'm PMRF PhD scholar from IIT Madras. I'm PMRF NPTEL TA for the course EMI, EMC and Signal Integrity. So this is 11th live problem solving session. The course is taken by Professor Amitabha Bhattacharya from IIT Kharagpur. So like we are doing for the last 10 weeks, we will be solving few problems which are related to this current week's assignment problems. So let's start with the question number one. If you have any doubt, please uh, you can unmute yourself or ask me, or you can also type in the chat.
Okay, sir.
Thank you. So we will start with question number one. So this week's was like week 11's lectures were relatively simple because most like theoretical stuff was also there. So some of the questions will be not numerical; they will be like statement wise, like which of the statement is correct kind of a questions will be there. So we'll start with question number one. Considering far field sources, the skin depth, just a second. Uh, so considering the far field sources, the skin depth, reflection loss and absorption loss for a 3 millimeter thick nickel whose permeability and relative conductivity here is with respect to Cu, copper. Means with respect to copper, what is its relative conductivity? For nickel, it is 0.2. The thickness of this shield is nickel shield is given as 3 millimeters at 2 gigahertz is given by now. We have to find the skin depth, reflection loss, and absorption loss for a 3 thick. Means let's say there is a box or some electronic device which is contained inside this container or a shield which is made up of nickel whose thickness is 3 millimeters. Means the metal sheet thickness is 3 millimeters, and we have to find at the frequency 2 gigahertz. We have to find the skin depth delta, reflection loss RdB, and absorption loss AdB. All of these are for far field. So I hope the question is clear.
No, sir.
So we will move on to the solution. So uh, we know that for far field sources, so we have to use for far field formulas for this. For far field sources, skin depth is given by, so I'm directly writing the formula here because it will take some time if I derive it again. So I'm directly using the formula which has been derived by professor. So 0.06609, just a second. So those who have joined now, we just started with question number one. I will reread the question quickly. Considering far field sources, the skin depth, reflection loss, and absorption loss for a 3 millimeter thick nickel whose relative permeability is given and its relative conductivity, which is respect to the conductivity of copper. Because in EMI EMC they take it copper as a reference. So epsilon sigma r is with respect to the conductivity of copper, which is given as 0.2 for nickel. We have to find then the frequency is 2 gigahertz. So we have to find the skin depth, reflection loss RdB, and absorption loss AdB. So now for far field sources, we know that the reflection skin depth formula is 0.06609 divided by under root mu r sigma r into f. Now all these quantities are already given in the problem. We know what is mu r, which is 600 for nickel. Sigma r conductivity, relative conductivity is 0.2, and the frequency of operation is like the wave which is coming that we have to shield has a frequency of 2 gigahertz, 2 into 10 to the power 9. So when we solve it, we will get 0.00013 millimeters. So this is our skin depth for a nickel shield of 3 mm thickness. And now we have to find the reflection loss RdB, which is given by the formula. Again, I am just writing the direct formula here. 168. For far field it is 168.14 plus 10. Just a second. So we are solving question number 1. Considering far field sources, the skin depth, reflection loss, and absorption loss for a 3 mm thick nickel shield at 2 gigahertz is given by. So we have already found out what will be the skin depth for that nickel shield of 3 mm thickness. And now we are finding out what will be the reflection loss. So the formula is 168.14 plus 10 log 10 log 10 of sigma relative conductivity of nickel divided by mu r into the frequency. I will move on to the next page. So now we know what all these quantities are already given in the problem, so I will substitute it here. So 168.14 plus 10 log 10 of sigma r is given as 0.2, mu r is 600 into the frequency, which is 2 gigahertz. So it comes out to be 40.3585 decibels. So it shows that because of the reflections inside the metal, nickel, this much of the wave is attenuated because of the reflection. And now we have to find out the absorption losses inside the nickel for a far field. Means the wave which is coming out can be considered as coming out from a point source and which is far away from the uh, device under test, which can be placed inside this. Or maybe it is this nickel is a casing which contains the electronic components of a device. So now we are finding out the AdB, which is the absorption loss. So here these losses are good. We want to reduce that wave intensity as much as possible because it can cause interference. So AdB is given by, for a far field is, I'm again directly writing the formula, 131.4 into T. So here only the thickness part is coming in the absorption. Into T, where T is the thickness of the metal sheet, which is given as 3 millimeters, multiplied with under root F frequency sigma r into mu r. So now when we substitute this 131.4 into, so it's in millimeters, so we have to write it in meters, 0.003. The thickness is 3 mm into frequency, which is 2 into 10 to the power 9, 2 gigahertz, into sigma r is 0.2 and mu r is 600. So when we solve it, we will get 193, sorry, 1.93 into 10 to the power 5 decibels. So here if we see which kind of loss is more dominating here, because of absorption most of this wave is getting attenuated, because it is 1.93 into 10 to the power 5 decibels. Here the reflection losses are only 40.3585 decibels. So now we will match it with the given options. So we find out delta means skin depth was 0.00013 mm, 40 point. So the correct option is option C. I hope this question is clear, because it's just directly the formulas that we have to use. So the correct option is, it will be good if you just follow these questions whatever are given in the problems, like in the assignments, because in lecture 11 there are a lot of things in the slides, but I would suggest focus more on the questions which are there, like focus more on the formulas which are used in the questions in the assignment problems, because there is a high chance that those kind of questions only or those formulas will be important in the final exam, but a lot of other things are also there in the slides. So correct option is C. And if you solve few problems based on these, it will become easier to remember the formulas, because here if you start deriving the formula it will take long time, but if you just remember directly the final end form of these formulas, it will be easy directly, like you can just directly calculate it from these. So I hope this question number 1 is clear. We will move on to question number 2. Which of the following correctly describes the electric dipole and its near field characteristics? Four options are given. The question is asking which of these four, out of these four statements, correctly describes the electric dipole and its near field characteristics. Option A is the electric dipole is a low impedance source and its near field, and in its near field the wave impedance is less than the intrinsic impedance of the medium, uh, which is not true. Option B is the electric dipole is high impedance source. Yes, because electric dipole is not a low impedance source; it is a high impedance source, and it is in its near field the wave impedance is greater than the intrinsic impedance of the medium. Option C states that the electric dipole is a high impedance source, and in its near field the intrinsic impedance is greater than the wave impedance. Option D is the electric dipole is a low impedance source, and in its near field the wave impedance is equal to the intrinsic impedance of the medium. So in near field, in near field of the electric dipole, the wave impedance is greater than the intrinsic impedance of the medium. Therefore, electric dipole is referred to as a high impedance source. Or in the near field of near field of electric dipole the wave impedance that eta not of for a free space is 377 ohms, but for this eta hat or eta tilde is the near field wave impedance. In the near field of electric dipole, the wave impedance is greater than the intrinsic impedance of the medium. So if the medium is air, we will take eta naught, which is 377 ohms. Intrinsic impedance of the medium. Therefore, the electric dipole is referred to as high impedance source. Therefore, the electric dipole is referred to as a high impedance source. So if you match it with the given options, the correct option is option B. The electric dipole is high impedance source, and in its near field, the wave impedance is greater than the intrinsic impedance of the medium. I hope this question is clear. We will move on to question number 3. So now, if you are talking about transformers, a transformer is like a magnetic source. Because in the lectures we have seen the formulas for the electric and magnetic. So in the near field of a transformer means here, like it kind of in a magnetic source, near to a magnetic source, the magnetic field is proportional to 4 options are given. So it is asking about for a transformer we know it's a magnetic source. So the magnetic field is proportional to, we have seen that H, theta and E phi. Magnetic field is proportional to 1 by r cube and electric field is 1 by r square. We have seen in the lectures. So the transformer is because transformer is an example of magnetic source. And in near field of a magnetic source, the magnetic field is proportional to 1 by r cube and the electric field is proportional to 1 by r square. Now we will match it with the given options. So the correct option here is option number B. I hope question number 3 is clear. Now we will move on to question number 4. A very short wire in a switching power supply is modeled as an electric dipole. If the fundamental frequency of the switcher is 220 kHz, then the magnitude of the wave impedance of its radiated field at a distance 10 cm is given by. So here we have to find out ZW. A very short wire in a switching power supply is modeled as an electric dipole if the fundamental frequency of the switcher, like the wire is very short, so it is acting as a electric dipole, means it acting as a radiator like an antenna. So now we have to find out what is the wave impedance of its radiated field at a distance of 10 centimeter. So what is given in the question is the frequency is given 220 kilohertz. So that is from this we can find out beta naught, which is 2 pi by lambda. So lambda is C by F. So when we solve it, we will get 0.0046, and the distance R is given as 10 centimeters per meter, so it will be 0.1 meter, and ZW is given by 60 into lambda naught by R. So when we solve it, it comes out to be 8.18 into 10 to the power 5 ohms. Since all are given in this, so it will be 818 kilo ohms. So correct option is option number C. I hope this question is clear. If you have any doubt in this, please let me know.
Okay.
If it is clear, we will move on to question number 5. So in some question, if it is given as transformer, then we have to consider it as a magnetic source and use those formulas for that. So a transformer in a 220 kilohertz switching power supply is modeled as a small magnetic loop. So earlier we used this dipole as a electric source. Now this is a magnetic source. A transformer in a 220 kilohertz switching power supply is modeled as a small magnetic loop. So as a magnetic dipole. So the magnitude of the wave impedance of its radiated field at a distance 10 cm is given by. So here we have to find out ZWM, or simply ZW. So in the problem given is the frequency is given as 220 kilohertz. So again we can find out beta, since beta naught will be same here for the previous question. I'm just writing it again here as it comes out to be 0.0046, and the distance it is at a 10 centimeter away, so it will be 0.1 meter. So ZW is, so I'm directly writing the formula, which is 2369 R by lambda naught. So 369 into 0.1 divided by lambda naught, C by F, whatever it comes out to be, we will, so the final answer will be 0.1737 ohms. So now if we matched with the given option, the correct option is option A. Uh, I hope question number 5 is clear. If you have any doubt in this, please let me know. If it is fine, then we will
Okay.
move on to question number 6. So question number 6 is, the drawback of magnetic shielding is that the permeability of ferromagnetic materials decreases with increasing. So it's directly question from the lecture. We have seen that when the conductivity, so we have seen that that the permeability of ferromagnetic materials, it should be high, right? But when the frequency increases, it decreases. So what are the two things which because of which it decreases? So the first thing is frequency. When the frequency increases, the permeability of ferromagnetic materials decreases. And the second thing is, as the magnetic field strength increases, again the permeability of this ferromagnetic material decreases. So here the correct option is frequency and magnetic field strength. Correct option is option D. Because that's the reason that we are using steel casing only. Otherwise, there are very high permeability materials available. But as the frequency increases, there we have seen a plot where we have seen that their effect decreases after a while. And for steel, it is like kind of a constant. It doesn't vary with frequency and mu. So that's why, because these other materials are expensive, and it doesn't make sense at a high frequency to use them because their permeability is also same, so there will be a pretty similar shielding. So that's why the steel is used for a lot of shielding. So I hope this question is clear. The correct option here is D, because the ferromagnetic materials permeability decreases as the frequency increases, and also it decreases as the magnetic field strength increases. Now we will move on to question number 7. What is the formula for total effective shielding in practical scenarios? So in practical scenarios, in theoretically what we have seen is this shielding efficiency in dB for the theoretical analysis that professor has done in the lectures. We have used it only depends on the RDB, reflection, absorption, and MDB. But in practical, we have seen that nothing can be a complete filled box, like a complete box which surrounds everything. If you see our PC, like our CPUs, they have fans, they have Type C, Type A USB ports, and cooling vents are there. So there, this is theoretical analysis won't hold true because there will be leakage also. So in practical scenario, there is a leakage, has to account for leakage LDB along with reflection. RDB is reflection loss. ADB is the absorption loss inside the material or inside the sheet. Absorption loss. And MDB is a multiple reflection loss. There will be multiple reflections. Multiple reflections. So if we see which option accounts for the leakage also means LDB is only which accounts for all these four is option C. So the correct option here is option number C. And leakage, what it does, it's a negative thing, like it reduces the shielding efficiency. So reflection loss, absorption loss, and multiple reflections are adding up. Means they reduces the impedance, or like they attenuates the wave. But here leakage allows the wave to exit from it or enter the other wave. So it reduces the shielding efficiency. That's why it is minus LDB. So the correct option is option C. I hope this is clear. If you have
Yes,
any
sir.
doubt, please let me know. If it is clear, then we will move on to question number 8. In shielding, Webinet's principle states that, so what this Webnet's principle is, principle states that, so it relates the, so this Webnet's principle, it relates the fields of apertures to those of complementary dipoles. So that's why in lectures we have seen instead of having a big hole for vent or cooling, it's better to have multiple small holes because it allows lesser leakage. So in shielding, the question is asking in shielding, Webinet's principle states that electric and magnetic fields of a slot are complementary to those of a dipole. So the correct option is option number B.
Yes, sir.
Uh, so if this is clear, we will move on to question number 9. Question number 9, in question number 9, three statements are given and we have to find out which of the following are correct. So which of the following statements, just a second. So in question number 9, which of the following statements is correct for a magnetic source in terms of shielding? Statement 1 is absorption loss is unaffected by the type of sources. Statement 2 is reflection loss at near field is less than that of far field. Absorption loss is higher at lower frequencies. So in previous questions we have seen absorption loss, in lectures also we have seen that absorption loss is unaffected by the type of sources, means it can be electric or magnetic. It's true. Statement 1 is true. It's correct. Because absorption loss is not affected by the type of source. It can be a magnetic source, means a transformer, or it can be a small wire acting as an antenna, a wire antenna or a dipole antenna, as an electric source. So absorption loss is unaffected by the type of source. Statement 1 is true. Statement 2 is reflection loss at near field is less than that of a far field. That is also correct. So reflection loss in the near field is less than the far field for a magnetic source. Statement 2 is also true. Absorption loss is smaller at lower frequencies instead of higher. So for a magnetic source, absorption loss is small at lower frequencies. Because here I have seen like for 2 gigahertz, we have seen that absorption loss is much higher than that of reflection loss at a high frequency. So at lower frequencies it is smaller at lower frequencies. So absorption loss is smaller at lower frequencies. Reflection loss is higher at smaller frequencies compared to absorption loss. So statement 3 is incorrect. So if you match it with the given option, only option 1 and 2 are correct. So option C is correct. I hope this is clear. If you have any doubt, please let me know.
Okay, sir.
If this is clear, then we will move on to question number 10. So here, if you've seen, like all these questions are they not taking much time to solve. Only few problems are there where some calculations are there. But in lecture in week 11 and 12, the questions from these 2 weeks will be like kind of similar to this. Like most of the questions will be theoretical. Like you don't have to solve. Numerical problems will be less. Which of the following is correct regarding the radiated emission of a gap? So, which of the following is correct regarding the radiated emissions of a gap? Gap means like an aperture we can take. So that means you have to, it's talking about Webinet's principle. So from Webinet's principle, I will write down it here. From Webnet's principle, the length of the gap determines the radiated emission. The length of the gap determines the radiated emission of the gap. Just a second. So from Webnet's principle, the length of the gap determines the radiated emissions of the gap. Gap length is if it is in the order of half the wavelength, therefore the gap length is of the order of half wavelength, therefore the gap has the potential to radiate like a half wave dipole. Gap length is of the order of half wavelength, therefore the gap has the potential to radiate like a half wave dipole. So now we will match the given options. The thickness of a gap is more critical than its length in determining radiated emissions. A gap with a length of the order of half wavelength radiates similar to a half wave dipole antenna. So option B is correct. Option C, both thickness and length of a gap are equally important in determining the radiated emission. The thickness of the gap alone determines the radiated radiation potential. So the more important is the length of the gap. It determines the radiated emissions. So option B is correct. I hope this question is clear. If you have any doubt in this, please let me know. So if this
Okay.
is clear, we'll quickly go through week 10, like last week's some assignment problems. So there was some issue with the mic, so I will quickly go through all the questions. It won't take much time. So we will start with question number 1. So here consider the following statements. Crosstalk signal appears as pulses occurring during the transitions of the source voltages. Statement B is crosstalk coefficients for near end is always positive. Statement C, crosstalk coefficient for far end depends on the type of coupling which dominates either capacitive or inductive. So statement A says that as appears as a pulses, that is correct. Like whenever there is a transition happening in the clock signal or clock pulse, so crosstalk is directly proportional to the dV by dt and di by dt. So it appears only during rising and falling edges. What it means is, so let's suppose this is the clock pulse. I generally they are like a trapezoidal pulses. So that's what a practical clock pulse looks like. So if you see only during this rising and falling phase, let's say if this is voltage signal, so dV by dt will be some number here only, right? At this point it will be 0. So crosstalk only appears as a pulses. It will appear as a pulse during the transitions of the source voltage. Statement A is correct. Statement B states that the crosstalk coefficient for near end is always positive. Which is true, near end is always positive, so statement B is also correct. Statement C, crosstalk coefficient for far end depends on the type of coupling which dominates either capacitive or inductive. That is also correct. At far end, capacitive and inductive coupling acts in opposite directions. So when capacitive coupling dominates, it will have one polarity. If the inductive coupling dominates, it will have another polarity, like the opposite polarity. So statement C is also correct. So the correct option here is all the options are correct. So in question number 2, 3 and 4 the same data is there, means some same RS232 cable is there whose length is 4.737 meters. It is a 3 wire cable. We have to it is terminated by a 75 ohm load. The separation between the lines is 50 mils and the wire radius is 7.5 mils. A trapezoidal pulse train of 2 volt 20 kilohertz the frequency with a 50% duty cycle is given as input signal to that cable, whose rise time of this pulse trapezoidal pulse train, the rise time and fall time are equal as 400 nanoseconds. In question number 2 we have to determine the relative permittivity of the medium if the one-way transit time of the line is 22.4 nanoseconds, and we have to assume lossless and homogeneous medium. So epsilon r we have to find for the medium. So in the problem the line length is given, separation between the line means s is given, and the rw means the radius, wire radius of all these three wires is equal, which is 7.5 mils. And the amplitude source voltage amplitude Vs is 2 volts and the frequency is 20 kilohertz for that trapezoidal pulse train, and the duty cycle is given as 50%, that is tau by t is 0.5 and the rise time and fall time is same, and one way transit time td is given, which is td is length of the wire by the velocity of the wave. So here the medium we don't know, so the velocity will be given as c by under root epsilon r, where epsilon r is the relative permittivity of the medium. So since Td is given, length of the wire is given, and c is light speed of the electromagnetic wave in a free space, which is 3 into 10 to the power 8 meter per second. So only epsilon r is remaining, so we can find it out easily. So I hope question number 2 is clear. Similarly, in question number 3, we have to find the slew rate of the pulse. So slew rate is given by dvs by dt. So dvs by dt will be the rise time is already we know that fall time and rise time is 400 nanoseconds, means we have to find the slope. Basically slope we have to find. Let's say this is the trapezoidal pulse train. So its rise time is given as 400 nanoseconds and this peak voltage Vs is 2 volts. So the slope will be 2 by 400 nanoseconds, which is 5 into 10 to the power 6 volt per second. So the correct option is option B. So slew rate means the slope of this trapezoidal pulse. And in question number 4, if per unit length mutual inductance and capacitance of the line is 0.33 microhenry per meter and capacitance is 4.08 picofarad per meter respectively, we have to determine the near end voltage across receptor and reference conductor during transition. So we know that formula for near end inductive coupling coefficient is given by, so we have to find the inductive coupling coefficient and the near end capacitive coupling coefficient, and then the total coupling will be given as the sum of these three. The third one MNECI is the mutual coupling, like the combined effect of inductive and capacitive. So when we solve it, we will get MNE as 1.0904 something into 10 to the power 8, and the near end voltage across receptor and reference conductor during transmission is given by using this formula. So we have to multiply it with the slew rate. So when we solve it, we will get 54.5 millivolts. So here this question is like, so it will take some time to solve because a lot of calculations are there, but the formulas are direct. And in question number 5, two statements are given and we have to choose the correct one. The primary purpose of LISN is uh, line impedance stabilization network, is to prevent the external interference from contaminating the measurement. which is correct. Like that's why we use LISN to prevent external interference from contaminating the measurement. If you are using testing a device, let's say a device under test, some kind of a PC or some kind of a mobile phone, or like some kind of a device which is connected to the electrical grid. So we don't want the interference coming from the conducted wire or the grid to affect the measurement. We want to find out uh, the interfer or the EMI EMC effectiveness of the device. So we just want to avoid the contamination from the power grid. So that's why LISN is used. So statement A is correct. Statement B is this military standard 461 CE03 conducted emission is based on voltage. No, we have seen in the lectures that it is based on current. So only statement A is correct, because we have seen this in the lectures that this military standard, all the other CE and all these American standards and European standards for Class A and Class B devices are based on voltage, but this military standard is conducted emission standard is based on current instead of voltage. So the correct option is option A. Only statement A is correct. So same question number 6, 7, and 8 has the same like it has a common data, means it's the same RS232 cable is there, and the per unit length resistance of the line is given as 0.45 ohms per meter, and the per unit length mutual inductance and capacitance is also given, and the line length is 4.73 meters. The separation between the three cables is given, and the wire radius is given as 7.5 mils. Same trapezoidal pulse of 2 volts 25 kilohertz with 50% duty cycle is given as input signal, and they have the same rise time and fall time, which is 450 nanoseconds. So R and E, which is that near end resistance, far end resistance, and the load resistance, all are 50 ohms, and the source resistance is 0. So in question number 6, we have to determine near end common impedance coupling coefficient. That is, we have to find out MNE CI. So near common impedance, CI is the common impedance coupling coefficient. So the formula is given here. This R naught, capital R naught, is the total resistance, but we have only given in the problem is per unit length resistance. Sorry, resistance. So we have to multiply R naught with the length of the wire. So this is direct formula based question. And in question number 7, we have to determine the crosstalk at the far end when the time t is tau r. So for that we have to find uh, the voltage, which will be the sum of all these three, that is mutual inductive coupling coefficient, near far end inductive coupling, far end capacitive coupling, and the far end common impedance coupling coefficient. The sum of all these three, and then the voltage at far end is given by this multiplied with the slew rate. So I hope this question is clear. I have uploaded these slides. So in question number 8, we have to determine the crosstalk at the far end. Same thing, but here the time is t by 2. So I hope this is clear. In question number 9, which of the following statements are correct? Only two statements are given, and we have to find out which one is correct. So shielding is used to contain internal radiated emissions of the product. Yes, it prevents the external radiation to affect the device, as well as the internal radiation or the unwanted signal from the device should not go outside and affect the other devices nearby. So that is the shield. That's why shielding is done. So statement A states that shielding is used to contain internal radiated emission of the product, which is correct. Statement B is the primary purpose of line impedance stabilization network is to provide uniform impedance for the conducted emission measurement. So it's not the primary purpose. It's one of the purpose is a secondary purpose. The main purpose we have seen in here. The primary purpose of line impedance stabilization network is to prevent external interference from contaminating the measurement. So statement B is incorrect because it's not the primary purpose. It's the secondary purpose of LISN to provide uniform impedance for the conducted emission measurement. So only statement A is correct. And in question number 10, shielding effectiveness consists of. So we have seen in the lectures that shielding effectiveness consists of this RDB. It consists of this RDB means reflection loss, absorption loss, and the multiple reflections, that is MDB, happening inside the sheet or the metal. So always a good conductor is used as a shielding material. So the correct option is all of the above. So I hope this is clear. That's all for today's session. If you have any doubt, please let me know. It will be good if you just go through the textbook also once. Like, it contains a lot of things, but just don't go through everything. Just read the relevant chapters, uh, the things which have been discussed in the class. So once you have seen all the lectures, then if you read the textbook, it will become easier to understand. And if you have some time, you can try to solve the and exercise problems. That will help you to remember the formulas. So that's all for today's session. We will meet next week, Tuesday, same time, 6 to 8. If you have any
Okay,
doubt,
sir.
please
Thank
let me
you.
know. Otherwise, this is all for today's session. Thanks for joining. Thank you.
Thank you. Thank you, sir.
Thank you. Yeah, thank you. Thank you for joining. What do you mean?